Great. Thank you very much for the invitation. It's exciting to be here. So today I'll talk a little bit about a version of percolation on higher dimensional cell complexes instead of graphs. This is based on joint work with Matt Kahle at Ohio State and Ben Schweinhart at George Mason. Ben is here and will be giving a talk tomorrow on related topics. Okay, so let me start with a quick review of percolation, although it may already be familiar. So the idea of percolation models, right, is we take some graph and we remove some pieces of it at random and see what the properties of the remaining subgraph are. So for today, I'm going to be looking at bond percolation, where we're keeping all of the vertices and then throwing away some subset of the edges. So the simplest non-trivial model here is an independent subgraph. So we have all of the vertices, and then for each edge, we flip a coin, a biased coin with probability p, to decide whether to keep that edge or throw it away. And so then the probability of ending up with a given subgraph will be p to the number of edges of the subgraph and times 1 minus p to the number of missing edges. So, of course, in the independent model, there are already many interesting questions. But actually, for today, I want to focus on a dependent model and its higher dimensional generalization. So the random cluster model starts with a similar formula. We have p to the number of edges, 1 minus p to the number of missing edges, but then we add an additional term that weights this model by the number of connected components. So we have q to the c of h. Again, c of h is the connected components. And so I'm going to focus on the case where q is at least 1. So this has a nice property that the edges are positively associated. So if we're thinking about whether an edge should be open or not, it'll be, if the rest of the graph is set up so that the endpoints of the edge are in the same component, then we just add this edge with probability p. But if we're joining two components, then we're paying a cost of q. So when q is greater than or equal to 1, having other edges helps us avoid paying this additional cost. So they're positively correlated. And of course, this is a generalization of the independent model that I just talked about. When q equals 1, this last term disappears, and we just have the independent model. So this model is of interest because it's connected to the Ising and Potts models of magnetism. I won't talk about that today. And of course, this definition I just gave only makes sense in a finite graph, right? Because we're counting the number of connected components. But of course, this can be extended to infinite graphs via limits. And the prototypical graph for all of these percolation models is often the integer lattice ZD. And this will be the setting as well for the higher dimensional model that I'll talk about in a second. Okay, so if we want to move to higher dimensions, so a graph kind of has 0-dimensional vertices and then 1-dimensional edges. So we want to add maybe something 2-dimensional. And this was done by Eisenman, Chase, Froelich, and Russo when they introduced plaquette percolation. So a plaquette is just one of these 2-dimensional cells. So they considered the integer lattice Z3, cubical lattice. And then the cubical lattice the natural two-dimensional cells are the unit squares, right, with integer endpoints, so just the faces of the cubes in the cubical lattice. Okay, so you can easily define an independent model here. So here we're going to add all of the vertices and all of the edges, and then some subset of these unit squares, these plaquettes. So we end up with some complex that looks something like this, and then we can ask what kind of properties this has, whether it has a nice phase transition similar to classical percolation. And actually, I'm going to go one step further and define not only a higher dimensional model, but a higher dimensional dependent model that we're going to call the plaquette random cluster model. So we want to add some additional dependence in a way that also connects to statistical physics in a nice way. Okay, so I'm going to need to do a quick detour into just the basics of algebraic topology. It turns out the natural definition of this dependent model goes through homology. So the kind of key notion here is the boundary map, right? So in the case of edges, the boundary just maps an edge to the difference of the endpoints of that edge. And there's also a boundary map on plaquettes as well. So if I fix some orientation of one of these plaquettes, you can sensibly talk about the boundary as a sum of the edges going around this plaquette oriented as so. And of course, we can extend this linearly, so the boundary of a sum of edges or plaquettes will just be the sum of the boundaries. So here I have an example with a few plaquettes, and you can see that there are arrows going in both directions along these internal edges, right? So we're adding an edge and then adding the edge going the opposite direction, so we get cancellation. So it should fit with your usual intuition that the boundary of all of these is just the kind of external boundary of the 2x2 square. Right? For an example with edges, say, if we have some path of oriented edges, then the boundary of this path is just the difference of the endpoints here. Okay, and so using this boundary map, we form a few groups that turn out to be useful. So the first group is just the boundary group. So we'll fix, we're studying formal sums of these cells with coefficients in a group G. We can just think of Z mod n for the moment. And so the boundary group will be a subgroup of just all the formal sums that comes from the boundaries of higher dimensional cells. So again, for a concrete example, right, the boundaries of the plaquettes here, each square boundary will, sorry, the set of the square boundaries will generate this boundary group. Okay, another group we're interested in is the cycle group, which is the sums that have zero boundary. As the name indicates, in the graph case, the cycles are just the loops in the graph. Right? If instead of a path here, I closed it up to form a loop, then all of a sudden we're getting cancellation everywhere, and this thing has no boundary. And the boundary of these plaquettes, each boundary is itself a loop, so it's not hard to check that the boundary group is a subgroup of the cycle group. And this leads to the definition of homology, where we take the quotient of the cycles by the boundaries. Okay, so why is this useful in this setting? So the zeroth homology.
Could you show the H definition again?
Yeah.
It's very quick.
Yeah, so I'll do an example in a second. Yeah, maybe I'll do it now. So the easiest homology group to compute is the zeroth homology. So the boundary of a vertex, I haven't said, but we just defined to be 0. And so then here we're just left with all the vertices, but then we're modding out by these boundaries. And so the boundary, right, if two vertices are connected, there's some path between them. And so that path is telling us in this quotient that those two vertices are equivalent. So the zeroth homology group will just look like the rank will be the number of connected components. So if we chose coefficients in Z mod Q, for example, then the size of this group would be Q to the number of connected components. Or on each connected component, we choose some coefficient. And of course, this Q to the number of connected components is just the weighting term that we saw a second ago in the random cluster model, which should indicate, maybe if we want to go to higher dimensions, we should use a similar weighting, except maybe we want to use a higher dimensional homology group. Okay, so that's what we do. So for the plaquette random cluster model, we have this independent percolation piece, and then we additionally weight by the homology group, the size of the homology group in dimension 1 lower than the plaquettes. So if we have 2-dimensional plaquettes, we're weighting by H1, which again, just for concreteness, is the cycle space, the graph cycle space, modulo the boundaries of plaquettes. So the cycles that are filled by plaquettes disappear, and if I had 2 cycles that were connected by a tube, then those would be equivalent. So that's what we should have in mind here. Okay. So it turns out this model is also connected to a physics model. It's connected to a version of lattice gauge theory. And so if that sounds interesting, I recommend going to Ben Schweinhart's talk tomorrow. He talks more about that application. For today, I'm just going to focus on the properties of the complex itself and see what we can see there. So, okay, it's all well and good to define a model, but what are the right questions about it? I think there are many questions, but the most straightforward one is just what's the generalization of the usual percolation phase transition. So, right, the study of percolation kind of centers around the appearance of a giant or an infinite component. And it's a little bit tricky to find the right definition of right generalization, rather, of an infinite component in these higher dimensional models. Of course, the way that I defined it by putting in all the vertices and the edges will make it connected, so it doesn't make as much sense to talk about connected components. And for various reasons, it seems like we should be looking for a higher dimensional invariant rather than just the number of connected components. So in all of ZD, I'd say it's an interesting open problem what the right phase transition should be. But we can say a little bit more if we move to a compact approximation of ZD instead. So that's what I'm going to do for this talk. So I'm going to look at a large torus. So we can take a large cube in ZD and identify the opposite sides. which forms the torus, and the torus inherits the cell structure from ZD. Right, so we have the same lattice in a neighborhood. Of course, it'll look the same, but the space overall is compact. So let's think about what percolation should look like in this torus. Maybe as a warm-up, we can start with the usual version of graph percolation. And here we can't have an infinite connected component, but we can have maybe a global component in some sense, right? So if in the full lattice I have an infinite component, then you would expect if I did percolation on a torus, there would be a component that's big enough to see the global structure of the torus, right? And so the way we're going to formalize that is look for a component that has a loop that kind of spans the torus. Here I have an example in a continuum model where if I put together this blue path and then this red path, we get a path that kind of spans it in the horizontal direction. So if I have such a path, then as the size of the torus increases, the size of the path and its component will necessarily increase as well. Right? So this is our approximation. And to distinguish, of course, there are also loops that would be considered local, right? There's no sense in which this is a global loop. To distinguish those local loops and the global loops, it turns out, again, these boundary notions from topology are useful. So these local loops, both of them are boundaries of some union of squares. Right, here, this is a boundary of one square. Here, this is a boundary of four squares together. But when we have this loop that spans the torus, you can check that this is not the boundary of any set of squares. In fact, this is the cycle is an element of the homology of the full torus when we fill everything in. So precisely, so we say a cycle is giant if when we do this inclusion, right, any cycle here will also be a cycle over here, but some of them disappear because of the larger boundary group. So if it survives this inclusion map, then we say this is a giant cycle. Okay. So this will be our notion of percolation that works in higher dimensions as well. Okay, right, so if I have two-dimensional plaquettes, now I'm going to look for a giant two-cycle. And here's an example of what one of these looks like. So this is the three-dimensional cube with the opposite sides identified. And here I have some union of plaquettes. And you can kind of see this is like approximately a sheet stretched across two of the coordinate directions. Again, it's not hard to verify that this is not the boundary now of any set of three-dimensional cubes. So this is a notion of a global two-dimensional object. Of course, there are many possible witnesses for a giant cycle. We could perturb one, like we've done here. Right? If I kind of move a little piece of this around a little bit, it will still be a giant cycle. But there's this equivalence relation that we just defined. So we want to say that giant cycles are more or less the same if they differ up to a boundary in the torus. And so the rank of the homology group in the torus is D choose I. So this can be seen because the first homology of the torus is just generated by the loops starting from 0 going in each coordinate direction. If some of those, they'll tell us all of the possible giant loops. And then for higher dimensional giant cycles, it turns out these, by the Kuhn formula from topology, since the torus is a product space, the giant cycles are products of these loops. So in this case, this giant 2 cycle here is the product of the loop, the Z loop and the X loop, say. Okay. Okay, so this will give us D choose I. And so that lets us kind of say at some point we have we've seen a representative for all of the possible giant cycles, which will be useful in a second. So to state the main theorem, I'm going to define 2 events here. So A is going to be the event that P has a giant cycle. So this is in homology with coefficients in a field F. So the coefficients here may not necessarily be the same as the coefficients for the definition of the random cluster model from a second ago. And S will be the event that we have representatives from all equivalence classes of giant cycles so that this map is surjective. So here, again, is an example. The dimension of this giant cycle space is 2. We kind of have the horizontal giant cycle and the vertical one. And so as I mentioned before, the red and the blue give us the horizontal giant cycle. And then the green and then the red will give us a second linearly independent giant cycle. So here we have a surjective map. Okay, so now we can state the theorem, and it's a little bit cumbersome to state, but more or less what we prove is that there's a sharp threshold for the appearance of these giant cycles, and that at that point we go from having none of them to all of them. A priori, it may not be a constant threshold. It could be a threshold that depends on the size of the torus. So we're taking n going to infinity and saying the threshold is getting sharper there. We expect that there should just be a constant threshold for the appearance of all these giant cycles. And kind of the highlight here is in the half-dimensional case, not only is there a constant threshold, but we can compute exactly what it is. So it's this root q over 1 plus root q. So for example, if we have 2-dimensional plaquettes in 4 dimensions, this is exactly the threshold for the appearance of giant cycles here. Yeah.
Do you know in other cases when it's not d over 2, that this lambda function does not blow up with the n, so it stays tight, doesn't go to 0 or to infinity?
Yeah, or so lambda is going to be between 0 and 1. This is like the p-value. But yeah, we can bound it away from 0 and 1 using some estimates. So there are some relationships between different dimensions. I haven't stated everything we prove here, but you can imagine, so if you have a 2-dimensional lattice and a 3-dimensional lattice, it's going to be easier to percolate in the 3-dimensional lattice. There are relations like this, so you can use those to bound it away from 0 and 1.
Very nice.
Yep.
Sorry, what is Q?
Q is the parameter for the plaquette random cluster model. So it's the kind of the strength of the weighting based on the homology group.
So it's Q to the size of the homology group? Is
Yeah. Or it's the size of the homology group with coefficients in Z mod Q. Or Q to the rank. It's the same when Q is prime, but yeah, it's the size of the homology group in general.
So,
And this lambda function does depend on the field F that you put in addition?
Yes. So there are, if we change the field F, maybe we can see things like non-orientable giant cycles. So those could appear at different thresholds potentially.
And your Q has to be integer, right? unlike the usual random cluster.
Yeah, so you can, if you want to keep the connection with the lattice gauge theory, then Q should be an integer. There are ways you could define it similar to the random cluster model for different values of Q, but to have that connection, yeah. Okay. Yeah.
Sorry, I'm confused about the difference between the field F and Z mod Q. They're different things?
Yeah, so there are two different kind of homology groups we're talking about. So one is informing the distribution for the complex, and that's the Z mod Q. And then there's another one where we're looking for a transition. So I could, once I choose my model, I could look for all different kinds of giant cycles. You know, they don't have to necessarily match up. Maybe I can see a non-orientable giant cycle in a model that's based on the homology with Q equals 3, say. Yeah, thanks for the question.
But your lambda on the bottom one even does not seem to depend on the choice of F, or?
Right, so in this half-dimensional case, things are very nice.
But you expect this to not be the general case?
We can't necessarily prove it.
No, but do you have some hunch?
I'm not sure exactly what to think. I mean, yeah, of course you can like construct examples where it's a giant cycle of one type but not another. But usually the way these, I mean, right, when percolation occurs in a graph, a lot of things happen. You go from having very small components to maybe a unique infinite component in a lot of cases. So it's possible that none of these distinctions matter, and once things coalesce, then you see everything at once. But yeah, formally they're kind of different objects. So I'm not sure. If I had to guess, I would guess that everything appears at once, but I don't know. Yeah.
You restricted to Q greater or equal to 2, so this is because of the proof? Or is
I'm sorry, this is a mistake. So the character of F should be not equal to 2. Forget about the Q greater than or equal to 2. This is for an integer Q. It's at least 1. Yeah, or greater than or equal to 1. Yeah, thank you. Okay. Great. So with the time we have left here, I'll just talk a little bit about how we prove this. Yeah, actually, how much time do I have left? I got a little bit scrambled by the
You have half an
schedule.
hour.
Okay.
Plenty of time.
Okay, good. Okay, so we have a few different pieces here. So for the half-dimensional threshold, the main tool we use is a duality between these different complexes, and actually we can use that to say a little bit more about what these lambdas should be, which I'll talk about in a second. The second piece we're using here is some action of the symmetries of the torus. So this is relating finding one giant cycle to finding all of them. And then the last thing we need is some general sharp threshold result. So this torus is very symmetric. So, excuse me, it turns out that many increasing functions, like the appearance of some object, will have a sharp threshold. Okay, so kind of part of the motivation for starting this project was to take this nice duality relationship that has been used to great effect for percolation in the plane and trying to understand that in higher dimensions. So the famous example is the square lattice. So here I have the square lattice in black, and I'm forming the dual graph where we have a dual vertex at the center of each face of this square lattice, and dual edges between adjacent faces. And of course, it quickly becomes apparent that this dual graph is the same as the square lattice itself, and it turns out this is quite powerful in the context of percolation, because if I take some subgraph of the black graph, there's a natural choice of subgraph of the gray graph as well, where for each edge, dual edge pair, I take exactly one or the other. So I take my subgraph here, and then I kind of take the complementary dual subgraph. So in the context of independent percolation, we have percolation with probability p is giving us a dual percolation with probability 1 minus p. So this is used in the Harris-Keston theorem to show that the critical probability should be 1/2 because it's self-dual. And in the random cluster model, there's a similar situation. The dual graph has the nice property that it is essentially a random cluster model as well, maybe up to boundary conditions. And this was also used more recently to show that the critical probability for the random cluster model on Z2 in the plane is the self-dual point. So there's some other function here that tells us what the dual p parameter is. So the fixed point for this function is the critical probability for the random cluster model on the square lattice, and that's actually the same value I just gave a second ago for our general half-dimensional model. So we can think of it as an extension of that work. And so this relationship also extends to higher dimensions. So here I have something in 3 dimensions. I have the cubical lattice, and then I have the dual lattice. Same deal, we have a vertex at the center of each face, edges between adjacent vertices, and there's a pairing between 2 plaquettes and dual edges. And so if I take, say, the plaquette random cluster model here, again, an indication that this is the right way to think about it is that the dual to the plaquette random cluster model is the graph random cluster model in 3 dimensions. And yeah, so we can do the same thing in the torus up to some constant factor that won't change the phase transition that's appearing here.
What does it mean up to? So the probability density of a given complex is not exactly that of the random cluster.
Yeah, so essentially what's happening in the torus, there's kind of a correspondence between the homology of the graph and the homology of the dual complex. And so the correspondence is a little bit nicer when there aren't these giant cycles. There are a few extra terms, but it's just a constant number of them. Okay, and so our main tool to compare this model and dual model is some version of the topological lemma used to prove the Harris-Keston theorem about crossings of rectangles. So the way they showed that there's no percolation at p equals 1/2, again, this is the kind of self-dual point for the independent model, is to show that there are crossings of arbitrarily large almost squares with a fixed probability here. And the heart of this lemma is this picture where I have an n by n+1 rectangle here, and I can kind of overlay it with an n+1 by n rectangle. And because of how we've set it up so that these two things are complementary, you can check that there has to be exactly one of a vertical crossing here or a horizontal crossing here. They kind of interfere with each other, but there must be one or the other. And this is essentially proven by inflating both of these graphs, like two balloons, and you can follow the interface between them. If you end up on, you start in the corner. If you end up on the right side, that's a horizontal crossing in one of them, and if you end up on the bottom, that's a vertical crossing in the other. So in the torus, it's kind of morally the same situation. You have some crossings of some kind, and they're kind of distributed between the two models. So I'll make that more precise here. So I'll add one more event. So we had A, that there's any giant cycle, S, that there's all of the giant cycles. I'll add Z, that there are no giant cycles. And so if we have the black dot here, this is the event in the dual complex. So the total number of giant cycles in the torus, remember, is D choose I. And so the key lemma here is that the sum of the ranks of these two giant cycle spaces is D. So in particular, we have to have a giant cycle in one piece or the other. And if we have all of the giant cycles in the primal model, then we have none of the giant cycles in the dual model, and vice versa. So yeah, I won't get into too much detail here, but this is essentially done in a similar way. So if we inflate both of these complexes, we can kind of fill the whole torus. And then there are some nice results in algebraic topology where if we have some manifold and it's a union of two subspaces, then you can say something about the topology of those subspaces. So here you can say that they have to exhibit all of the giant cycles between them. Okay, so that's the duality part. So now I'll get to the sharp threshold part. So, oops, okay, sorry, I'm again missing a piece. So the character of this coefficient field should not be equal to 2. Sorry about that. So with that assumption, this is saying that if we have one giant cycle with constant probability, then we can have all of the giant cycles with some constant probability, where the relationship between these constants only depends on the dimension of the torus. So you can imagine if we have one of the generators for the giant cycle space, say one of the loops going around the torus, the symmetries of the torus can take that loop to another loop, right? Because we can permute the coordinates in ZD, that'll permute the coordinates in the torus. So one generator can become another. Since there's this nice positive association property, we can bound the probability that we have all of these in terms of the probability that we have one. And so then we would be done, right? We would have all of the entire giant cycle space with some probability bounded below. But we have to be a little bit careful here because we might not be given a giant cycle in the form of one of the standard generators. It might be a sum of those. And here we can get into a little bit of trouble. So yeah, let me draw the three-dimensional torus here. So say the three generators are A, B, and C. So what if I start with something like A plus B? So this would be a giant cycle that goes across here diagonally somehow, right? And I start doing my symmetry tricks. So I can turn this, for example, into A plus C by switching B and C. I can turn it into B plus C. And if we're doing homology over most fields, these are enough to generate the space. Because we can add things together, we can get 2A plus B plus C, and then subtract B plus C, and then get just 2A. So when the characteristic is not 2, then this will generate the whole space. But if the characteristic is 2, it turns out there is this invariant subspace that I've just given. We have to be careful. So a priori, there could be 2 transitions. First, where we see this invariant subspace, and then another where we see actually all of the giant cycles. So this is, I guess, connected to the question from before. Should these actually be different thresholds? I would say probably not, because I would guess that it's more difficult to produce something of the form A plus B than it is just A. But yeah, again, it's hard to rule these out at this point.
But if your giant cycle was A plus B plus C and you did these permutations, wouldn't you just be a fixed one?
Right. We can also we can also reverse one of the directions. This is another symmetry of the torus. So that's a good point. So that'll handle that, but again, that won't help us mod 2. So yeah, it ends up coming down to some question about whether a representation is irreducible, and mod 2 it is not necessarily. Okay, and then the last piece here is this general sharp threshold theorem. So there's a large theory on sharp thresholds for Boolean functions. Often the statements are for product measures. So there's a result of Freegood and Kahle saying that if there's a symmetric increasing event for a product measure, then it has a sharp threshold. So we are in that setting, right? Because using the translations and the rotations of the torus, we can map any plaquette to any other plaquette. So they all should have the same influence. And it turns out this sharp threshold concept extends even to positively associated measures. There's a result of Graham and Grimmett. So these kinds of events in the torus also have sharp thresholds. Okay, so just quickly to put this together. So we take some p-value lambda so that we see a giant cycle with some positive probability, say 1/2. And so this will give us a version of the threshold, because we use this symmetry lemma to see all of the giant cycles with some positive probability. So if both of these probabilities are bounded away from 0 and these events have sharp thresholds, then they have the same sharp threshold. And then we can use this duality lemma to say a little bit more. So the dual models, since when we see all of the giant cycles in one model, we see none of them in the other, we can take the lambda for the d minus I model, the complementary dimension, to be the dual parameter, this p star for the I-dimensional model. So in particular, when something is self-dual, this has to occur at the self-dual parameter. So yeah, this is just kind of scratching the surface of this model. There are many more interesting questions. The most obvious being, what happens in the full lattice. So by working on the torus, maybe we can say that we can build large sheets of some kind in the lattice as well, but there isn't an obvious way, for example, to generalize the notion of a positive density component in the full lattice. So many questions remain here, including also some quantitative ones. So another question you can ask about these models in the lattice is the probability that they fill a particular loop. And again, I'm going to advertise Ben's talk here. He'll talk a little bit about that. That's a physically relevant parameter, and we can say something there as well. Okay, so that covers what I wanted to say. Thank you.